All right, now how exciting. We're finally on to supermassive black holes. What do we mean by supermassive? Well, we'll get to that. What evidence is there for supermassive black holes at the centers of galaxies? And do supermassive black holes have any role? It says regulate. It says regulate. That's a bit strong, perhaps. Do they have a role in galaxy evolution? I'll bet you the answer is yes. I'm jumping ahead in the first slide, showing you talking to you about quasars, which were discovered. I think the first one might have been 1960. Active galactic nuclei. That's the nucleus of a galaxy. Very bright galactic centers with jets. I wonder if that's a formal definition. So here's an AGN, and there's the jet. Wow. There's probably some sort of cocoon around the jet that confines it. That's a detail. So they were called quasi-stellar radio sources because when they were discovered in 1960, no one knew how far away they were. And so they looked like stars, and they were radio sources. They're the brightest of the AGN. It's a temporary stage of galaxy evolution. Found at great distances, billions of light years. By the way, quasar was a TV, went out of business. Zenith made the, I don't know. So bright that they swamped the light of their host galaxies. So there's a galaxy in here somewhere. Somewhere in the middle of that is a galaxy. I don't know what the scale is on this. There's a galaxy in there, but we don't see the galaxy. We see the light from the quasar. And there's a supermassive black hole that's powering, and with an accretion disk, that's where the energy is coming from. This happens to be M87, another famous one, Virgo A or NGC 4486. That's the Messier list. That's the catalog that I have a slide. I think in this module, yes. And that's the constellation that it's in. All three names for the same object. So there's the active galactic nucleus, singular here. There's the jet. And so we have a general definition. If the center is unusually bright, we call it active galactic nucleus. Quasars being the most luminous. The interesting thing about quasars, aside from their great brightness, is that they contain matter over a wide range of temperatures, which means we can observe them at many different wavelengths. Remember, most stars and galaxies emit primarily invisible light, but the quasars can give you energy at many different wavelengths. There's a slide, but I didn't show it to you. This slide, however, I want to show you because this is just so way cool. This is an actual redshift. So let's find a line. This is 3C273. Here's, let's see, let's find H delta. Okay, here's H delta. Here's H delta. This is the comparison spectrum. This is Z equals 0, redshift. And look where it is over here. Woohoo. So there's a shift of that much. Let's see, let's take another one. Let's look at H beta. Here's H beta. We'll change colors. Here's H beta here, and H beta is here. So it looks like the shift is about the same. So what is this shift? How big is that shift? Well, if that's about, let's say, that's about 500 nanometers, and that's about 600 nanometers. And so what would you say? That's 5 minutes, 100 right there. It's about 2/3. So it's about, let's just make it easy. So 70 nanometers. Remember, the redshift Z is delta lambda over lambda. So it's about 70 nanometers is the shift. The wavelength is about 500. So it's 7/50th, so it's nearby, right? Geez, it's what, 7 out of 50, it's about 0.15. I made the 1415, right? So it's not what we'd call today a big one. What's a big one? Over 1. But still, it's pretty cool. It's all relative, what you mean by highly redshift. My usual thing about numbers are big or small, only in comparison to other numbers. So back in the day, when quasars were found, that was a decent size redshift. And here's the other thing I wanted to show in this slide, is that the variability shows that all this energy comes from a region smaller than our solar system. We're talking black hole. How does that work? Well, because light travel time says that I can only see variability over the time that light can traverse a region. I can't see variability over a region that the light can't come across. So it gives me constraint of how big the volume is. So what can you conclude? This is a great thought question. What can you conclude from the fact that quasars usually have very large redshifts? They're generally very distant. Yeah, I would say that corresponds to very large redshifts. They were more common early in time, yes, since look back time corresponds to, redshift, yeah. Galaxy collisions might turn them on. We just had a module where we talked a lot about galaxy collisions, so that's possible. Nearby galaxies might hold dead quasars. Why not? They're going to evolve. They're going to turn off. Geez, there's a 4 million solar mass black hole in our galaxy. Could we be a dead quasar? Probably not, because we're going to find out that the black holes in the quasars are quite a bit bigger. So all those are true, by the way. They are, in fact, supermassive. I'm going to show this slide quickly. I'm not going to talk about it much, except to show you this. This is the amazing thing, because this is a model. And look, you should, again, talking about how much you've learned, it says here, the mass of the central black hole can be calculated with Newton's version of Kepler's third law. So you know that from the orbit of molecular clouds around the black hole. And so you do the calculation, and you see the dots there, and the dots there, and the dots there, and they're right on the theoretical calculation. And so this models 36 million solar masses. The black hole at the center of our galaxy is about 4, so this is of order 10 times ours. This is a composite image showing visible light, X-rays, and radio waves, so it shows that there's a lot going on. This is M106, and it says here that the radio wave showed jets of energetic plasma are shooting out from the center of the galaxy. Ooh, there's lots of stuff going on. X-rays show those jets are heating gases above and below the galaxy disk. Let me give you so you can see that. Look at that right there. Okay, there's a lot of stuff going on when you have a 36. You're going to see 36 million. Here's a supermassive one. Again, great evidence. Blue shifted spectrum from one side of the active nucleus indicates rotation. Indicate a black hole with a massive, this is a 2 to 3 by 10 to the 9 solar masses. A billion, okay? In other words, about 1,000 times the mass of the Milky Way black hole, okay, which is about 4 million. This is 2 to 3 billion solar masses. But look, that's one estimate. Orbs of stars in direct imaging indicates a mass closer to 6. What's a factor of 2 between friends, though? We don't care about that. So when we talk about supermassive, we're often talking about billion solar mass black holes at the center of active galactic nuclei. So probably not our sun. This is a quick module. Many nearby galaxies, perhaps all of them, but not ours, supermassive black holes at their centers. They seem to be dormant. Why dormant? Because they began a long time ago, near the start of the universe, and now we're 14 billion years later. I don't know when they formed, maybe 4 billion years, say. So maybe they were only 10 billion years old or something, but at least that, because our own solar system is our own solar system is 4.5 billion years old. So, and here's the thing. All galaxies may have passed through a quasar-like stage earlier in time. So even our own galaxy, which has only a 4 million solar mass black hole, maybe we were a baby quasar. Here's another cool thing. We can plot the mass of the central bulge in solar masses versus the mass of the central black hole, also, of course, in solar masses. Look at this, 10 to the 5. Hey, we're bigger than that. We're about 4 million, right? So we got to plot on the log scale, and I think that's about 0.6. Log of 4 is about 0.6, so it's there. So we're here, right? And the mass of our central bulge, I had to look it up. 10 to the 10 solar masses. Shoop. So we're about there. So we're pretty close. I mean, look at they're not on the line. You wouldn't expect it to be on line, but there clearly is a relationship between the mass of the black hole and the mass of the central bulge. And so the development of the central black hole, this is my word. I should say factors. Factors in galaxy evolution. It's not clear how, but it seems to have some influence. I think, remember, early on it said regulate, and I didn't like that word, but it certainly factors in. This is a great graph, by the way. Now, I just have a bunch of pretty pictures that they're just so cool. I've shown you this cool one. The only reason I'm showing you this again is now this has a scale on it that says that's 500,000 light years. This is the one we estimated. So let's see if we can do a similar estimate like that. That's about 500,000. That's about another 500,000. We didn't do too badly, right? What do you say? 1, 2, 3, 4. It's about of order 2 million light years. Maybe we should do that. 2 by 10 to the 6 light years. We estimated. Remember, we just guessed from the center size of the galaxy. And like I said, the number I see in the on the web was, I think it said 1.5, but it wasn't clear if they meant that distance, in which case the 2 would be 3. I'm willing to believe that because it's not clear, how far it goes out, how far the lobe goes out. The point is it's big. Remember, our galaxy is 100,000 light years. Milky Way. That's 10 to the 5. This is of order 2 million. So it's more than 10 times our galaxy. And we're not that bad. We're not that small galaxy. Here's another picture. I'm just showing you the pictures on this one. It's a composite image. Look at this. Here's the galaxy. And look at all this stuff out here. The X-rays are blue, of course, the hot gas. Radio waves are orange. Right? There's a jet somewhere in there. And the elliptical galaxy, the dark streaks here. So we got cold, dusty gas. And it says, it suggests its experience emerged within the last few hundred million years. Yesterday. I mean, it's just, this morning. It's such a nearby time. We know that. We've already established that the lobes can extend over hundreds of thousands of light years. I wanted to show you this picture quickly to show June 1991, November 1997. It's only 6 years. Here's the AGN, right? And it's shooting out blobs, and you're seeing the blobs move in real time. That's how fast they're going, because they're moving at nearly the speed of light. This is material, massive material. Are these amazing structures? Aren't you glad you took the course just to see these pictures? Finally, I just had to mention this to you, the new general catalog. This is just from Wikipedia. Catalog of deep sky objects compiled by John Louis Emile Dreyer in 1888. Did you know that? Expanding upon the works of Herschel. One of the satellites was named after Herschel. William and Caroline Herschel and John's General Catalog of Nebula and Clusters. 7, almost 8,000 objects. Dreyer published 2 supplements in 1895 and 1908. A further 5,000 astronomical objects. So Newton said, if I've done great things, it's because I've stood on the shoulders of giants. Astronomy is very lucky to have dedicated people who spent a lot of their time in their lives just cataloging things. Morphological astronomy. We learn from the shapes. We learn from the objects. So that's a great contribution. Here's an amazing picture. Here's another 100,000 light years, so it's not nearly as big. This is just our galaxy, right there. What's going on here? Look at this. Why is it swept back like that? Well, what does it look like? It's going through intergalactic gas, the IgM. So remember, I was saying it doesn't cycle, but there is gas. There is gas there, and it's having an effect on the lobes that are coming out of NGC 1265. One other point I wanted to make about viewing effects of AGN. Radio galaxies do not look like quasars because they're kind of edge on, right? Here's seeing the edge. To see the quasar, probably what you need to see is the jet. So if you're over here, you might see, did I draw that correctly? You might see it as a quasar because you see the jet coming at you. But the AGN are concealed by gas and dust. So when you see them as face on instead of edge on, here's the edge. You see them face on instead of edge on, you might see them as a quasar. Who cares? They're gorgeous anyway. What have we learned? The evidence of supermassive black holes. The AGN are very bright objects. Best explained, the variability keeps it small by material falling onto the supermassive black holes. The orbits strongly suggest black holes. Great modeling. Great agreement with theory. With theory that you know about. With Newton's version of Kepler's third law. Do they regulate galaxy evolution? Possibly they regulate the galaxy's gas supply, and it certainly seems they do affect the bulge somehow, some ways. Perhaps strong, but maybe not. If they do something to, you can imagine that, right? There's a little black hole sitting here, a lot of materials falling in. Who knows? detailed calculations. But the point is there's an influence on the evolution because of the black holes. Okay, thank you. I think we've got one module left to talk about the gas in between galaxies.